Hello, class. Hello there. Are you saying that because I look like a Jedi with my Jedi hood, and that's what Obi-Wan Kenobi says? Hello there. Hmm. Okay, I'm gonna go ahead and get started. Hope everyone's doing well today. So I want to begin by reminding you guys a little bit about last time. So you might recall that I had originally planned for all this to be one lesson, but I decided that it was a little bit too much for one lesson, especially on the week of our midterm. So I split it into two lessons. So this lesson is going to teach you how to do the last questions 2 and 3 in the quiz that you didn't know how to do last time. Okay. So last time we discussed torque, which is denoted by the Greek letter tau. And the picture you want to have in your head when you're thinking about torque is you have some blob, and the blob has a pivot point. Maybe the pivot point is right there. And then you apply a force on the blob. Let's say you apply a force right there, and the force is maybe in this direction. Okay? So what you do is you draw a line segment that goes from the pivot point to where you're applying the force, and you measure the length of that line segment, and that's called R. And now that that line segment is defined, we can define the perpendicular to that line segment. Okay, so perpendicular to that line segment is like in this direction. Okay, and then we take our force and we use trigonometry to get the component of the force vector that is perpendicular to that line segment. So that's called F perp. Okay, and then the torque is calculated as R times F perp. If a torque would tend to rotate the object counterclockwise, then that is a positive torque. If the torque would tend to rotate the thing clockwise, then that is a negative torque. So I invite you to type into the chat if you know the answer. Is this force that I have drawn right here, is it exerting a positive torque or a negative torque on the blob? Type into the chat if you know the answer. And then we also defined the net torque, which is the sum of the individual torques that are acting on the object. Some of these could be positive, some of them could be negative. And we talked about how if the net torque is 0, then there is going to be no rotation. Someone has typed into the chat negative for the sign of this torque, and that is correct. Okay, so the way you do it, so if you might be able to just visualize it. Like, to me, it's obvious which way this is going to rotate. But if it's not obvious to you, what I would recommend doing is just grabbing anything close to you and setting it on your piece of paper or whatever, and putting your finger down to represent the pivot point. So now this calculator is pivoting around that point. And then just apply a force on the object. So this is representing the blob. And I can see that the force is kind of applied vertically up and to the left of the pivot. So I apply a force vertically up and to the left of the pivot, and I can see that it's rotating in the clockwise sense when I do that. So that would be a negative torque. All right? Or my hands are cold. So that is basically what we did last time. All right? Today's lesson, I'm going to talk about 3 different things, each thing building on the previous. So the first thing I want to talk about is something called center of mass. All right. And I'm not going to teach you how to calculate the center of mass today. I'm going to do that in a future lesson, in maybe like 2 or 3 lessons from now. But I'm just going to teach you conceptually what is the center of mass right now, and then we'll learn how to actually calculate it later. The center of mass is typically denoted by xcm, and it is, if you want to think about it intuitively, it is the average location of mass within an object. Okay? So if you have a blob, like say this is the blob, the center of mass is typically indicated as, it sort of looks like the BMW symbol. So this is the engineering symbol for center of mass. A circle with kind of like a checkered circle. Okay. Your center of mass may or may not correspond with the pivot point. So the pivot point could be someplace else. All right. Center of mass and pivot point are not necessarily in the same location. You could put the pivot point at the center of mass, but that, that doesn't always happen. So an important thing, if you have a uniform object, so for example, a uniform rod. So when I say uniform, I mean an object that has the same density throughout. Okay? If you have a uniform rod, then there's going to be an equal amount of mass on each side. You get what I'm saying? So the center of mass is going to correspond to the geometrical center of the object. Okay? So in the special case of a uniform rod, now not all things are uniform, but if you have a uniform thing that's symmetrical, you can say that the center of mass is actually in the geometric center. So if you have like a disc, and the disc is uniform, it's the same thickness throughout, it's made out of the same material throughout, then the center of mass is going to be in the middle of the disc. All right? If you have something that is non-uniform, so for example, a non-uniform rod, so what would a non-uniform rod be like? It would be a rod where maybe it's made out of a material where the density increases the further you go to the right side. Okay, so I'm trying to draw sort of a gradation in the density. So we have less dense over here, more dense over here. Do that, makes it look a little better. Okay, so in this case, there's more mass on the right-hand side because it's denser on that side. So what that's going to do is it's going to end up shifting the center of mass closer, closer to that side. Okay, so in the case now for today's lesson, we're going to be talking about a uniform rod. So the uniform thing. So the center of mass is always going to be actually in the middle. But if you have a non-uniform thing, which we'll talk about later on in the class, you have to actually calculate where it is. One way to experimentally determine the center of mass is to find the balance point. So the balance, another way of thinking about the center of mass is it's the balance point of the object. So what you can try to do if you're trying to find where the center of mass is. Let me see if I can find something that's... I'll be right back, class. I'm going to grab a baseball bat. All right, so I have a baseball bat right here. The baseball bat obviously has more mass on the end, the end that you're not holding on to. That's the more massive end of the baseball bat. So if I want to find where is the center of mass of the baseball bat, I just try and balance it from different locations. Okay, so you see if I balance it right here, it swings in this direction. So that means that the center of mass is more that way. So I move my finger there. Now it wants to go the opposite direction, so I move my finger again. And eventually, so that's pretty close. You know you're really close when it doesn't move very quickly. It doesn't tip very quickly. So it's like right there. Okay, somewhere around there, really close. So we can see that because this is not uniform, the center of mass is not in the geometric center of the baseball bat. It's more to one side than the other. Okay. So we can always find the center of mass by just trying to balance something at different locations. All right. So now on that note, I guess I'm not done with this baseball bat yet. If you try to hold something, so if I pinch the baseball bat, for example, at this end, and I let it go, it swings. It does that. So why does it rotate in that case? Well, it's because there's a torque on the baseball bat, and that is the torque due to gravity. So gravity exerts a torque, all right? So that's the next thing I want to talk about is the what's called the gravitational torque. And that's the torque due to the gravitational force. Which, of course, is also known as the weight force. Okay? So let's suppose we have a uniform rod. Okay? So let's consider a uniform rod of mass m and length L. Okay. So here's the rod. And let's suppose that the rod is pivoting about its left end. So you've drilled a little hole in the left end and you're allowing it to pivot around that point. Okay, because it is a uniform rod, the center of mass is going to be in the middle. So now the question is, if we're calculating the gravitational torque, we know the size of the gravitational force. The gravitational force is mg, right? The gravitational force is mg. But so the main question when we're calculating the gravitational torque is what R value should we use? Okay. And so the lesson here is that when calculating the gravitational torque, you can treat the weight force as if it is concentrated at the center of mass. Okay, so that is that's the main thing you want to remember when thinking about the gravitational torque. Okay, so I know the center of mass is here, so I can put the weight force, which is mg, right there at that location. Okay, so notice that that then allows me to figure out what the R value is. Okay, because the total length is L, and the center of mass is here. So the distance from the pivot to the center of mass is L over 2. So the R value I would use in this case is L over 2. And then the size of the force is mg, because it's the weight force. All right. Notice that because this rod is horizontal, the weight force is perpendicular. All right. The weight force is perpendicular. And so we don't have to do any trigonometry to get, the component of the weight force that is perpendicular to the rod. It's already perpendicular. Okay. So in general, the torque due to gravity is going to be the distance to the center of mass times the component of the weight force that is perpendicular to that line connecting the pivot to the center of mass. So that's in general. All right. So I would like to ask a question, which is, what if the location of the pivot is equal to the location of the center of mass? Okay, so what if you had a rod where its center of mass is here, and you put the pivot right there as well? What R value would you use in this case? If the pivot and the center of mass coincide, what R value would you use when calculating the gravitational torque? Go ahead and type it into the chat if you know the answer. I'm going to close the window really fast because I'm freezing. Excellent. Yes. So I see several of you have typed in 0, and that's the correct answer. So if the pivot is equal to the center of mass, okay, then the R value is 0, which means that the gravitational torque is equal to 0. Okay? So that explains why when you hold something from its center of mass, it balances. Okay? Because when you're holding something from the center of mass, there's no gravitational torque, and so the thing doesn't rotate. It just stays put. It balances. If you hold it from a spot that is not the center of mass, then now there's a non-zero R value, and so the thing will start to rotate. Okay? Which leads me to my next point, which is when does the object stop rotating? And why does it stop rotating? Why does the bat swing vertical? Okay? It turns out that an object will swing to a spot where the center of mass is directly below the pivot. Okay, so that's a useful piece of information. Why is that? Well, if you think about it, okay, so it's going to swing to a location where the center of mass is directly below the pivot. Why is that? Well, let's say the center of mass is right here. Then the line connecting the pivot to the center of mass is vertical. Okay, there's a vertical line connecting the pivot to the center of mass. And then the weight force is also vertical. So you can see that the line and the weight force are parallel to each other in that case. So what that means is that F perp is 0, which means that there is, again, no torque. All right? So that's what, so basically, if you hold something and you let it swing and come to rest, you know that the center of mass is directly below where you're holding it. Okay? So I think that's an interesting piece of information. Maybe you don't, but I do. Okay. So that gets me to my last topic for today, which is the most important topic for today, and that is static equilibrium. Okay, so an object is in static equilibrium if the object is not translating and not rotating. So we don't have translation and we don't have rotation. It's not translating and it's not rotating. Okay? So why is that the case? So what I wanted to first of all talk about, what is translation versus rotation. So translation means moving from place to place without changing the orientation. So this is examples of me translating the calculator. Okay, I'm translating it. It's moving around, its orientation is not changing. So this would be translating, but not rotating. Okay? To be rotating means the orientation is changing. Something like this. but it's not moving as a whole. So see how the calculator is generally staying in place, but its orientation is changing, okay? So this is translating. This is rotating. You can have both simultaneously, okay? That would be something that looks like this. So this is translating and rotating, okay? But if you're not translating and you're not rotating, then that means you are perfectly still, right? And so that's why static equilibrium is really useful for engineers. Engineers design structures to be in static equilibrium. Okay, if you make a building and it's not in static equilibrium, that's really bad. Okay, so engineers, mechanical engineers, are thinking about static equilibrium all the time. So what does it mean if you are not translating? Well, not translating means that the net force on the object is equal to 0. Okay? Because if the net force were not equal to 0, it would be accelerating from place to place. Okay? If the object is not rotating, then that means that the net torque is equal to 0. Okay? Because torque controls rotations. So these two equations have to be true in order to be in static equilibrium. So I'm going to call these the conditions for static equilibrium. These are the conditions for static equilibrium. And so because these are two equations, you end up getting a system of equations when you're solving static equilibrium problems. And I'll show you how that works in just a moment. One thing that's nice about static equilibrium, if we think about the pivot point, in general, the pivot point is the only spot on the object that is not moving when something is rotating. Okay? See that? The pivot point is the point that doesn't move when the thing is rotating. All right? If something is in static equilibrium, then every spot is not moving because it's perfectly still. So that means that where the pivot point is doesn't matter. So in a static equilibrium problem, you get to choose the pivot point. All right? You can choose it to be at any location you want it to be. I will, in just a second, I'm going to provide a suggestion for where you should put the pivot point. But in general, you choose the pivot point. You choose where the pivot point is. All right? And so that's only for a static equilibrium problem because the entire thing is not moving. So let's do an example and see how this works. All right? Let's suppose we have a uniform rod of mass m, mass 5 kilograms, and length 10 meters, is supported by 2 ropes. One rope is at the right end. The other is 2 meters from the left end. Okay, So let me draw a picture of this. So we've got a uniform rod. Because it's uniform, its center of mass is in the geometrical center of it. All right. And we know that the weight force acts as if it were going through the center of mass. The weight force is going to be 5 times gravity, which would be 50 newtons. And then there's a rope right here on the right end, and there's a rope 2 meters from the left end. So this distance right here is 2 meters. And then there's another rope, okay? So what I would like to do is calculate the tension in each rope. Okay, so each of these ropes is pulling up on the rod. Now the rod is hovering, so there's no normal force involved here. Okay, it's suspended by these 2 ropes. And I'm going to call the left tension T sub L and the right tension T sub R. So first of all, I have to choose a pivot point. All right. And what I recommend doing is choose your pivot point to be at the location of one of the forces. Okay. So I'm going to choose my pivot point to be right there. There's my pivot. That's my recommendation. You can solve the problem either way, but it just makes it simpler mathematically when you do it this way. Okay. And I'll talk in just a second about why that is. So let's go ahead and apply the first equation of static equilibrium. The net force, and this is going to be the net force in the y direction because all of the forces are vertical, so that there are no forces in the x direction. So I already have net force in the x direction equals 0. The net force in the y direction is going to be my up forces minus my down forces. So I have 2 up forces, TL plus TR, and 1 down force, which is 50. So minus 50. And that has to equal 0. Okay, that's the first condition of static equilibrium. So this is my first equation. Notice how I can't solve this equation because it has 2 unknowns. So that's why I need the second equation. It's going to turn it into a system of equations that I can solve. Okay? Now I have the net torque is equal to 0. Now, so now I'm going to return to this idea of why did I choose the pivot point to be at the location of one of the forces, okay? And the reason is when I choose the pivot point to be right here, so remember the formula for torque is R times F perp. What is going to be the R value for this force? Well, it's acting at the pivot point, so R is equal to 0. So I get 0 times the force. So see how that force is going to be eliminated from that equation. So that makes it easier mathematically. Then I have a gravitational torque. Who can tell me? Type it into the chat if you know. What is the R value I should use for the gravitational torque? Okay. Type it in if you know what R value should I use for the gravitational torque. And then I'm going to think about what is the sign of the gravitational torque. Well, the pivot is right here, and the gravitational force is acting downward. I can see that that rotates it in the clockwise sense. So gravity is exerting a negative torque. Excellent. Someone typed in 3 into the chat, and that is correct. Why? Because the rod is 10 meters long. So the center of mass is 5 meters from the left end, and this is 2 meters. So the remaining distance to the center is 3 meters. Okay. So pivot to center of mass is 3 meters. Type it into the chat if you know what is the R value you should use for the tension due to the right rope. Okay, so while I write this down, so the R value for the gravitational torque is 3, and the gravitational force is 50. It's already perpendicular, so I don't have to worry about trigonometry. Okay, so lastly, I have the torque due to the right rope. Okay, and the right rope I can see is pushing up, and I can see that makes the rod go in the counterclockwise sense, so that is a positive torque. And the answer that was typed into the chat is correct. You would use R equals 8 meters for the right rope because the total length is 10. This length right here is 2. So the remaining length is 8 meters to the point of application of that force. So I plus 8 times the force, which is T sub R. The force is perpendicular, so I don't need to do trigonometry. Okay? So this is my second equation. So now you notice I have 2 equations and 2 unknowns. I can solve it. So I'm going to go ahead and work on this second equation. So 0 times T sub L is just 0. 3 times 50 is 150. So that is my second equation simplified. And that says that T sub R is equal to 150 over 8. 150 over 8 is 18.75 newtons. So that is the right tension. Okay? That is the right tension. Now, when you're solving a system of equations, if you get one of the variables, you then re-plug it in to the other equation to get the second variable. So I'm going to plug that in for T sub R. And I will rewrite this equation down here. So I have T sub L plus 18.75 minus 50 equals 0. And this says that the left tension is 31.25 newtons. Okay. So there you have it. One of the things that one of the things you'll notice here is that the left tension is greater than the right tension. So why was that in this case? Whichever rope is closer to the center of mass is going to be the one that is carrying more of the weight. Okay. So that's kind of an interesting point. So this rope would need to be stronger than that rope. All right. There's one other thing that I wanted to talk about. So I'm not going to do a full example, but what if the center of mass is at an unknown location? What if the center of mass is at an unknown location? Let's suppose we have a rod, and it's a non-uniform rod, so the center of mass is not going to be at the geometric center. Okay, And this rod has 2 ropes at each end. Okay. This rope is 30 newtons, carries 30 newtons of tension, and this rope carries 50 newtons of tension. Okay, and the total length of this rod is, let's say, 2 meters. Okay. So we know that there's a gravitational force acting from the center of mass. All right. We just don't know where it is. So let's just go ahead and give it a variable. Let's just call it x. So I'm going to say that the gravitational torque is, I'm taking my pivot to be the left end, and the center of mass is just some distance x from the left end. Okay. Now, you might say, well, I'm not telling you the mass of the rod, but we can actually very easily tell what the mass of the rod is. It's got to be 80 newtons, right? Because the total amount of upward force is 80 newtons. So that means that the weight of the rod has to be 80 newtons. Otherwise, the rod would be going into the air or sinking into the ground. Okay? So now we apply the conditions of net torque equals 0. The torque due to this 50 Newton force is 0 because it is acting at the pivot point. The torque due to gravity is going to be negative x times 80. So distance times force. And it's rotating it in the clockwise sense. And then the torque due to this force on the right end is going to be plus 2 times 30. All right. So we can take this equation and we can solve for x. And we can determine where the center of mass is. All right. So that's pretty nice. So these are basically the 2 examples that are on the quiz that you don't know how to do. So now you know how to do them. That's my lesson for today, and I will see you in the Zoom room.